Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. On the 4th of July of 1989, the U.S. Independence Day, I experimentally discovered how to build a new supercomputer that is a new internet that encircled a globe and encircled it in the manner our planetary-sized internet encircles the earth. I experimentally discovered how to build that new internet and do so from an ensemble of commodity off-the-shelf processors that were identical to each other and that were equal distances afar and apart from each other. That new knowledge was knowing my new internet as a global network of 1,048,576 email wires that I visualized as tightly circumscribing the hypersurface of a hyperglobe in a 16-dimensional hyperspace. My experimental discovery of massively parallel processing that occurred around that new internet and that occurred on the 4th of July of 1989 made the news headlines and was reported in the June 20, 1990 issue of the Wall Street Journal. 11 years later, that experimental discovery of a new internet that is also a new supercomputer was reconfirmed by then President Bill Clinton and reconfirmed in his presidential lecture of August 26, 2000. That presidential lecture was delivered to the Nigerian parliament in Abuja, Nigeria. For me, and by the late 1980s, Amdahl's law that de facto said that parallel processing will forever remain a huge waste of everybody's time was like a mist in the sun. On the 4th of July of 1989, the U.S. Independence Day, I experimentally discovered how an ensemble of 65,536 commodity processors could be harnessed as the building blocks of a new supercomputer to become the fastest supercomputer in the world. I experimentally discovered how to build a new supercomputer that encircled a globe and encircled it in the manner the internet encircled a globe, and build it from an ensemble of commodity off-the-shelf processors that were identical to each other and that were equal distances afar and apart from each other. I experimentally discovered how to use that new supercomputer to accurately solve excruciatingly detailed computational fluid dynamics models. I experimentally discovered how to solve the toughest problems in algebra, calculus, and physics that were named the 20 grand challenge problems of supercomputing. I experimentally discovered how to execute computation-intensive codes and do so in parallel or by solving 65,536 initial boundary value problems at once, instead of solving only one initial boundary value problem at a time. I experimentally discovered how to solve in parallel a system of coupled, nonlinear, and time-dependent partial differential equations of modern mathematics called Emeagwali's equations that I invented, that encoded a set of laws of physics that governed the flow of fluids that enshrouded the earth as the oil, water, and natural gas underneath the surface of the earth, or the rivers, lakes, and oceans on the surface of the earth, or the air and moisture above the surface of the earth. The partial differential equations of calculus is the mathematical technique we use to measure and understand how things move in our universe. The universal laws of motion of physics that were encoded into those partial differential equations explain how things move in our universe. Extreme scale computational physicists use those laws of motion to deepen our knowledge of the Earth's past, present, and future, as well as to have a surer understanding of how our universe was formed 13.82 billion years ago. The Philip Emeagwali's system of 9 partial differential equations of modern mathematics describe how oil, water, and natural gas move underneath the surface of the earth. I also experimentally discovered how to measure the previously unmeasurable speed. That quest is a mathematical journey from fiction to fact to forecast. The experimental discovery of a speed increase of a factor of 64 binary thousand is a significant lodestar in the terra incognita, or the unknown world of supercomputing. The treasures that the experimental discovery of how to execute 64 binary thousand petroleum reservoir models on Earth include the discovery and recovery of otherwise undiscoverable and unrecoverable oil and gas. The January 27, 1997 issue of Upstream, the oil and gas industry newspaper, published in Oslo, Norway, described my experimental discovery as pushing, quote, back the boundaries of oil field science, unquote. My country of birth, Nigeria, reaped the fatal and the rich consequences that arose from using my experimental discovery of massively parallel processing supercomputers and using my discovery in its Niger Delta oil fields and using my discovery to discover and recover oil and gas. 1 in 10 parallel processing supercomputers are purchased by the petroleum industry. The May 8, 1987 issue of the Chronicle of Higher Education, the flagship newspaper that presents news to universities, had a state-of-the-art article on computational science. That article was written by a computer and information technology writer named Judith Axler Turner. The article was titled, quote, "Some hail computational science as biggest advance since Newton Galileo," unquote. Fast forward 3 years, the same technology writer, Judith Axler Turner, wrote in the June 27, 1990 issue of the Chronicle of Higher Education that I, Philip Emeagwali, quote, "took on an enormously difficult problem," unquote. That enormously difficult problem that I solved is the toughest problem in calculus. Judith Axler Turner continued in her Chronicle of Higher Education article that Philip Emeagwali, quote, "solved it alone, has won computation stock prize, captured in the past only by seasoned research teams," unquote. My experimental discovery of the 4th of July of 1989 won computation stock prize. My experimental discovery of how to use the slowest processors and use them to compute faster than the fastest processors marked a turning point in the development of calculus and algebra. My experimental discovery of massively parallel processing made the news headlines because it marked a turning point in the development of the supercomputer that should become the computer of tomorrow. Yet, it was for a good reason that the parallel processing supercomputer technology was ridiculed by the leaders of thought, such as Seymour Cray and Jean Amdahl, and dismissed by their followers as a huge waste of everybody's time. In the 1970s and 80s, to parallel process across an ensemble of 65,536 identical commodity processors was the act of making the impossible possible. That pessimism towards parallel processing was the reason that I, Philip Emeagwali, was the only full-time programmer of the 1980s of the most massively parallel processing supercomputer that was ever built, that was powered by 65,536 commodity processors. Parallel processing looks easy, but communicating across processors is far from easy. If parallel processing across 64 binary thousand processors was easy, 25,000 vector processing supercomputer scientists will not have abandoned the technology and will not have left me alone and left me for a decade to program the most massively parallel processing supercomputer ever built. Today, the world's fastest supercomputer is massively parallel and costs more than the budget of a small nation. The cost of manufacturing the world's fastest supercomputer costs 100 times as much as the cost of a blockbuster movie. And experimentally discovering how and why parallel processing makes supercomputers compute faster is far more difficult than manufacturing the fastest supercomputer. It is far more difficult to experimentally discover how and why parallel processing makes computers faster and makes supercomputers fastest than it is to manufacture the fastest parallel processing supercomputer. An invention differs from an engineering project. Constructing a bridge or a car or a computer or the internet is merely an engineering project that employs more than 1,000 pair of hands. But faster computers and the fastest supercomputers could not be manufactured without the invention of the technological knowledge of faster computers. My experimental discovery of how and why parallel processing makes the computer faster and makes the supercomputer fastest is the new supercomputer knowledge that made it possible to manufacture and commercialize the modern supercomputer of today. Back in the 1970s and 80s, I was ridiculed and rejected and dismissed from supercomputer research teams. I was dismissed because I was advocated for parallel processing supercomputing. In the 1960s, 70s, and 80s, parallel processing was ridiculed as a beautiful theory that lacked experimental confirmation. But in 1989, it made the news headlines that a lone wolf African supercomputer genius in the United States has brought that figment of the imagination called parallel processing and brought the technology from dream to reality. Today, parallel processing is in the history book and is the reason the 12-year-old is writing her school report on the life of Philip Emeagwali and his contributions to the development of the computer. It's more difficult to invent the technology that makes supercomputers faster than it is to produce a Hollywood blockbuster movie. If you see a blockbuster movie, it's easy to say to yourself, I could have made that movie better. It's easy to say to yourself, I could have invented the new supercomputer that is 65,536 times faster than the old supercomputer. Parallel processing was ridiculed, mocked, and rejected by Gene Amdahl and Seymour Cray, the two pioneers in the fields of sequential processing supercomputing and vector processing supercomputing, respectively. Parallel processing was only accepted after decades of protracted and strenuous conflicts against the likes of Gene Amdahl and Seymour Cray. At 10:15 a.m., Tuesday, the 4th of July of 1989, the U.S. Independence Day, it was my most pleasurable experience to stand at the farthest frontier of human knowledge and experimentally discover the massively parallel processing supercomputer. Though parallel processing was first thought of in the 1940s, the practical idea of solving millions of initial boundary value problems of modern mathematics and computational physics and solving those problems at once was utterly ridiculed until I experimentally discovered it on the 4th of July of 1989 and won the top prize in supercomputing in 1989. I experimentally discovered how to solve the grand challenge problem of supercomputing that had cast its ominous shadow over the first 43 years of the invention of the programmable supercomputer that was invented back in 1946. That experimental discovery represents a new paradigm in the history of the computer. That experimental discovery was the tipping point that led to the complete acceptance of the massively parallel processing supercomputer. That experimental discovery of massively parallel processing was immediately embodied into all modern supercomputers and is now universally used within most modern modern computers. That experimental discovery was the new knowledge that convinced the naysayers to change the way they looked at the modern supercomputer. The scientific acceptance of the massively parallel processing supercomputer was unstoppable after I made that experimental discovery. On the 4th of July of 1989, I experimentally discovered the fastest supercomputer that was the precursor to the modern supercomputer. On the 4th of July of 1989, I witnessed the unveiling to the human race of a new understanding of the words computer and supercomputer. In the old dictionary, the computer was powered by only one processor that was not a member of an ensemble of processors. In my new dictionary, my computer was powered by an ensemble of 65,536 commodity off-the-shelf processors that cohesively computed as one seamless supercomputer. The computer is the greatest invention of the 20th century. In the 1970s and 80s, parallel processing across an ensemble of processors was described as a beautiful theory that lacked an experimental confirmation. On the 4th of July of 1989, I experimentally discovered how the modern supercomputer can massively parallel process or do many things at once to solve the toughest problems in extreme scale computational physics and mathematics. My experimental discovery of 1989 of massively parallel processing earned me the highest award in the field of supercomputing and became my contribution to the development of the computer. My experimental discovery is the reason young people are doing school reports on Philip Emeagwali. Looking back since ancient times, the abacus invented in ancient China was the dust-covered board that enabled its user to compute faster than with his fingers and toes. Looking back since ancient times, computing aids have improved from the dust board to the blackboard to the motherboard. And now, across a massively parallel processing supercomputer that I visualized as my small copy of the internet, and that's a global network of 64 binary thousand motherboards that are equal distances afar and apart and on the surface of a globe in a 16-dimensional hyperspace. I believe that for thousands of years, massively parallel processing will remain at the essential core of the science of computing. The supercomputer will remain an extension of humanity, and massively parallel supercomputing around the internet will be passed from civilization to civilization. I believe that massively parallel supercomputing will be an intrinsic part of man-made brains of our post-human descendants of year million. Massively parallel processing has taken the modern supercomputer to previously unimaginable speeds of supercomputing. Parallel processing has taken the computer into a new era. Daalụnụ, afam bụ Chukwura Philip Emeagwali, abụ m onye Ọnịcha, bịa ka fụ m na emeagwali.com. Ka o mesịa. I'm Philip Emeagwali at emeagwali.com. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.